Hello, everybody. Thanks for coming to Empower Our Futures. Empower Our Today, Empower Our Future is a Boulder-based coalition of organizations and individuals who support local clean power. Our mission is to move Boulder to 100% renewable electricity by 2030 in an electrical system that is more democratic, decentralized, competitive, and equitable than what we currently have under Xcel's monopoly here in Colorado. We also support other efforts to reduce greenhouse gas emissions. And while our primary focus is Boulder, we work at the local, state, and national levels and collaborate with and assist other communities as appropriate. And tonight, I am delighted to introduce Todd Pistorese. He's the founder and chief technology officer of SuperCap Energy, LLC. He's had a 36-year career spanning utility operations, finance, IT development, and management. From my understanding is that Todd is not having any problem telling you more about his background and history and telling us what's so super about SuperCaps. Thanks, Todd.
All right, thank you. Thank you, everybody, for coming. Okay, well, thank you, everybody, for tuning in. I'm an electrical engineer and have an MBA from University of Washington, and born and raised in the Pacific Northwest. I have a home on the Big Island in Hawaii, and piece of property in Telluride, Colorado that I seldom get to use myself because it's usually rented to people who enjoy skiing there. But I'd like to talk a little bit about how SuperCaps can help out in the effort to improve our situation and in renewables. Before I get into the actual slide set, I want to point out a couple of slides that are on this main screen. On the pictures on the lower left is a spot in Alaska that's a broadband repeater station, and that problem often gets well below -20 C in operation. It has a few SuperCaps in it. And then on the right is a telecom tower for one of the majors that is just outside of, on a mountaintop just outside of the Mojave Desert in California. And that sees temperatures often up to 50 degrees C. So we have a broad range of operation that we've placed these systems into, and we really think they have a place in the utility scale and all the way down to residential. So with that, let's move along. Oh, and I want to say thanks for joining me on St. Patrick's Day. So I've got my little clover in there for you guys. The agenda is pretty self-explanatory, but let me talk a couple of minutes about the takeaways. A significant increase in renewables is necessary. If we're going to get to where we want to be with reduced greenhouse gas, we have to change the way we do business. Large quantities of energy storage in order to make that work are mandatory, and we'll talk more about why that is the case, but best located near the loads end of renewable energy. Lithium batteries are needed for EV production to the extent that they can be directed that way. That would be the ultimate outcome. This discussion isn't about switching from lithium batteries to supercapacitors or some other type of energy storage. The demand for energy storage is so large, and I'm going to talk about that in the big picture, that we need everything that can be manufactured out there today to really have a chance at this. The supercapacitors are exceptional for stationary storage, and our supply chain needs quite a bit of attention. I'm sure all of you have heard some of the stories in the news about supply chain problems, and those definitely affect this industry as well. And at the end of the time, you can reach out to Empower. I'll provide a PDF copy of the presentation. I'm not going to go through the glossary of terms, but I added it here. So if you do download a copy of the presentation, you can always refer back to all these different pieces of jargon that are used. And I guess my one point I want to make is I'll talk about a number of things in some detail. The main point really is to understand the massive scale of what we need to accomplish, and really how we can bring that down to the level of each individual being the participant in this effort. So the energy storage spectrum, I mean, everybody knows about some of these storage types, and maybe some of you know about all of them, but hydroelectric's been around for nearly 100 years or more, and obviously that is something that we will continue to use to the extent it's available. I don't see any way that we build a lot more electric energy storage. Flow batteries and fuel cells are coming along. They have definitely niche applications. Everybody's experienced with alkaline and NiCad batteries. Those are the non-rechargeable type of batteries we use every day. And of course, lead acid batteries are in just about every vehicle that's out there as a starter battery. Interesting things happening over there. I got an email about this gravity energy storage where they'll lift these weights up and lower them down slowly, kind of like the weights in an old grandfather clock. So I put that clock picture in there as well. It's just simply a weight and gravity, and it's used to make things happen. But what we're really going to focus on today are the ones in yellow on the right hand side of your screen, the supercapacitors, and to some extent the lithium ion batteries. The real thing we're trying to get to here is kind of optimizing the best of two worlds. Everybody's familiar with some types of electrochemical batteries, whether those are the alkaline batteries in your flashlight or your TV control or lead acid battery, lithium ion batteries. They're all electrochemical in nature. Capacitors are electrostatic, at least for the most part. The early capacitors, which date over 100 years now, were just simply two plates of material, metallic material with a dielectric between them. The electric double layer capacitor is an advancement of that. It has activated carbon. Both sides, the anode and the cathode, are identical, and in such they exchange electrons electrostatically and have very, very, very long life cycles, maybe 1 million cycles in the life of a capacitor of this type. So they're noted for their power density. The ability to rapidly charge and discharge is the key feature of an EDLC. The lithium ion battery, on the other hand, is known for its energy density. Is probably the best chemical battery available these days to store energy. And it's a combination of graphite and some kind of a lithium-based compound using various other materials to optimize that capacity. What they're doing these days with supercapacitors, specifically the hybrid supercapacitor, is they share features from each of these products. The lithium battery provides the anode, which is a lithium carbon structure, and the electric double layer capacitor provides the cathode, which is the activated carbon side. There's some advantages of this. Predominantly what they do is they bring some of the features of the capacitor down, of power density, improved power density, some safety aspects, and some long life features, and some of the energy density capability of lithium. And you've probably seen or read about Benjamin Franklin's, little experiments with kites and keys, and I wouldn't recommend trying it, but that's all electrostatic. Now, there's a big trade-off between power and energy density. So on the chart on the right, there's the capacitors lie in the world of power density, and they can deliver energy very, very quickly, have very long lives, and have really been designed and used historically for that purpose, rapid discharge. Most every Energy Star refrigerator that's out there today has a capacitor that helps the motor start without a power surge, and it injects its energy very quickly to help that out. On the other end of the spectrum are batteries and fuel cells and those types of things that have high energy density, but are not designed to rapidly discharge. So energy density is the capacity of a device in watt hours per kilogram, and power density is a measurement of the rate of charge or discharge in watts per kilogram. And we'll talk a little bit about those things throughout the discussion. cycle life diminishes as energy density increases. There's some trade-offs there that we'll probably touch on, but suffice to say that supercapacitors tend to fall in that realm in between there. The goal is to enhance the energy density of a capacitor because of its features of long life and safety, and keep some of the power density features that they have as well. So there's some trade-offs. Electric vehicles are perfectly optimized for high energy density applications because you're looking for driving range. They trade off some of the safety capabilities, and you've seen Tesla cars catch on fire. It's pretty rare that those things happen, and they have diminished life cycles compared to capacitors. Stationary storage, on the other hand, doesn't have this need for high energy density in a compact space. And so you can take advantage of larger spaces so that this higher space requirement isn't an issue, and lower energy density is an applicable use for stationary energy storage. So we've put systems in, large and small. And in the upper left, we're about to do a project in the summer in well, maybe even sooner, in Panama, at this place called Isla Secas. It's an off-grid resort island that is about 1.1 megawatt hours of energy storage. They're currently running on lead acid batteries that have really ended their lives. And just below that is a small, more of a proof of concept high voltage system. That system runs at about 630 volts DC, which is a range of most of the utility inverters that are out there. And that's at an Everett, Washington design and fabrication facility. It runs a 40 kilowatt inverter. The one in the center is an off-grid heli skiing location in the Pedrillo Range of Alaska. It's about an hour and 10-minute flight by bush plane out to this site from Anchorage. And we swapped out about 15,000 pounds of lead acid batteries that were no longer functioning after about 3 years with 48 supercapacitors, and that had doubled their capacity in the same footprint, but it reduced their generation runtime significantly. Of course, when we got the generator run 24/7 because the batteries were no good. But when we left, the generator runs about 7 hours a day just to recharge the capacitors. We did add a few solar panels to where we could to help a bit, but I'd say in Alaska, that's probably the afternoon sun in the picture there. So that's, you can tell how low the sun is in the sky. Not much solar going on. The one in the center bottom is a nutritional manufacturer in Grand Rapids, Michigan, and their installation is really targeted at peak shaving. They're trying to mitigate their demand charge on their bill by using the supercapacitors to cut off the high demand pieces of their load. And then the one on the right is pretty typical. You see in a lot of residential places. It's on Whidbey Island, Washington. It's a small residential 8 kilowatt inverter, and it's designed to really back them up, but frequent outages happen on the island. So we need to transition away from coal-fired power. We have a bit of a luxury in the Pacific Northwest that 80% or more of our energy comes from hydroelectric. So we're a little bit ahead of the curve compared to Colorado. But the transition has to happen, and really the move is to either large-scale solar and large-scale wind. It would be nice to say we get more hydroelectric, but you guys know better than I do the situation with the Colorado River, and the refill has not been happening through these drought years that we've had for a number of years now. So Lake Powell's looking pretty unhappy these days. So significant energy storage is needed to make these work, and to make what the utility industry call these solar and wind farms to be dispatchable. The ability to call on them when they need them and use the energy storage to help make that happen. So when President Biden was elected, he proposed a 50% reduction in carbon emissions by 2030. And based on the 2005 measured carbon emissions, which were about 6,000 million metric tons of CO2, The target is going to be in the range of 3,000 million metric tons. But for our conversation here, it doesn't make much sense to talk about metric tons of carbon because that doesn't mean much to any of us. Just basically 1 kilowatt hour of energy from a coal plant is 0.9, almost 1 kilogram of carbon. And from a gas turbine is 0.5, so half a kilogram of carbon every kilowatt hour. The targets that we're going for are pretty much more than half come from utilities and transportation. And that's pretty consistent across the United States. The forecasted terawatt hours of supply from renewables for 2030 is only 500 terawatt hours. And a terawatt hour is a million megawatt hours. So it's a big number. And obviously that's the big shortfall in what is needed. And then the need is somewhere in the range of another 2,300 terawatt hours of generation from renewables. Colorado's component of that is about 70 terawatt hours of renewable energy. That's where you need to get to meet the 50% reduction target. There's a tremendous strain coming onto the utility grid based on EVs. I know there's a lot of efforts to put in rates that are designed to encourage people to charge their EVs during the low use times, late at night, midday, when there's a lot of renewable energy online. It's not practical for most people. It's, and I'll just show you in a minute, it's not practical at all for a lot of the EV fleet plans that are coming on board. But by 2030, we'll look for another 1,500 terawatt hours of EV requirement to cover the needs for meeting these kinds of renewable energy targets. The plan is pretty difficult because we're trying to catch up with what we already have in the fossil world, at the same time grow into a new world of electric vehicles. So the world has massive targets that they have to go after, and we'll see how that plays out. Just a conservative, a little bit about renewable energy and the problem and why energy storage is such a big deal these days. Conservatively speaking, about 40% of the production of solar is a mismatch with when the load occurs, and that may be very conservative. So midday solar, if you get to the Hawaiian Islands, the midday solar exceeds the load substantially, and the circuits will actually run backwards during the middle of the day when there's excess solar on the circuits. They don't have any place. If they don't have any place to use that energy, it just goes to waste. In California, they've curtailed solar generation fairly significantly in the last few years because of midday generation well exceeds what the loads require. So we need to move that somewhere else. And we estimate about 3 terawatt hours of daily on-demand energy storage are required for the United States. In 2020, the levelized cost of storage, and that's described as the total cost of the system with replacements and whatnot for a period of time divided by the number of kilowatt hours that come out of it, was 45 cents a kilowatt hour. The DOE's target for 2030 is 5 cents a kilowatt hour. We, because of the long life cycles, somewhere in the range of 500,000 or more cycles capable of the life of a supercapacitor, and with daily full charge and discharge cycles, we would levelized cost of storage today down to around 8 to 10 cents a kilowatt hour with the supercapacitors. The problem for the utilities and perhaps some of the residential or commercial businesses is to handle the amount of energy that EVs charging would require. 150 vehicle EV fleet on fast charge is 9.4 megawatts of demand. 18.8 megawatt hours of energy in that 2 hours would have to be pushed into these vehicles. That's about 18 20-foot containers of supercapacitors, in each of those containers 1.1 megawatt hour with daily cycling. And you would need 11,000 solar panels in an array in Colorado. In order to generate enough solar in the daytime to recharge those supercaps which would in turn be discharged into EV vehicles at night. So there's a big push for that. If it was left unattended without any storage to move this energy where it's needed, the utilities would have to significantly upgrade their distribution systems to carry the kind of energy for those short hours of demand, the 2 hours of demand that they're anticipating. To give it some perspective, the 18.8 megawatt hours of daily EV charge requirement equals 62% of a total typical Colorado residence for an entire year, and that's on a daily basis. So it's a massive amount of energy. If you look at the EV fleet a little differently, 150 EVs at rapid charge, which is the DC to DC connection called level 3, is equivalent to the demand from 234 high-rise buildings. So you can think of like all of downtown Denver's demand for a 2-hour window. The fleet, 150 fleet for a fast charge, which is level 2, and that's equivalent to a 50 amp welder or a residential oven type of a load. There's about 27 commercial buildings, and that same 150 EV fleet on a slow charge, which is kind of like run your extension cord out and plug it into your car at 110 volts, 120 volts, is equal to about 28 small buildings for 150 cars to be charged. This is a study that Scott Madden had done and published. So when we look at how energy can be used, folks put power walls into their homes. 90% of them are there for backup UPS power in case the lights go out. If you really want to move energy around, you need to cycle them daily, and that's not something you generally do to a power wall because it would rapidly diminish its cycle life. They have a limit in their warranties even on how many kilowatt hours you can put through the module in its lifetime under warranty. So it would take a 10-year warranty down to something in the range of 4.5 to 5 years if you cycled it daily. But you want to be able to do this because we want to be able to store energy in the daytime and then cover the loads in the evening. And I think a whole lot about, can I plug my electric vehicle in now or not? The MRM example I mentioned earlier is shown again on the right here. Their 15-minute average peak load is being mitigated. So essentially what happens is if the current that's demanded from the grid goes above a certain level that they define, it'll shave that off and cover it with the supercapacitors. And in Hawaii, they've offered up a program, and we cover it in the next slide, but they offer up a program where anybody who's willing to let the utility dispatch their energy storage for a 2-hour window in the evening is paid up to $850 per kilowatt of that system for the privilege for the utility to do so. And that's something they're looking for, something like 50,000 customers to participate in. 5,000 megawatts or not 5 megawatts, I think. I forget. So it's a program there that the utility is actually initiating, and I want to say that time use mitigation or peak shaving mitigation is useful for both, or beneficial for both the customer and the utility. The time use rates in Hawaii are fairly high. The midday, the daytime rates are down around 12 cents a kilowatt hour because there's excess solar, and the nighttime evening rates can reach 50 cents a kilowatt hour. So that swing is enough to justify moving energy around. And it has a really good return on investment. Demand savings are up to about 80% for this type of peak shaving approach, and could cut electric bills by at least 20% for time use. I guess the one point I want to make is you can be involved. You can get involved right away. I know that we wait to see what the utilities are going to do to solve some of these problems. We wait to see what the state's going to do to solve some of these problems. But really, other than offering incentives to the rest of us, we have to take hold of this on our own. I mentioned the utility plans in Hawaii. The feds, I think, are going to extend the investment tax credit, which if you put in solar, a storage with solar, the storage also qualifies for investment tax credits. I looked at the Xcel Energy's new time of use rates, and the differential isn't really large. I think daytime is 9 cents and the evening something up close to 15 cents. without any incentives, it's about a 15-year cost recovery to put storage in and do time of use arbitrage. But with incentives, that comes down appreciably, and that doesn't have any consideration for what future rate increases might occur. And I guess I heard that you've had rate increases for the last couple of years, so there's certainly going to be more rate increases in the future. The picture on the right of the states is ISLR's map of where these where solar plus storage is cheaper than the electric utility rates today. So you can see California is not surprising. Hawaii, Alaska, those places have fairly high electric rates. Colorado's not far off. I mean, your rates are high enough to justify solar plus storage. And in the long term, on levelized cost basis, it could be cheaper than utility-based service. The picture on the lower right is my system in Hawaii. It's 4 supercapacitors with an 8 kilowatt inverter and another 7 kilowatts of solar inverters. So we all know about your needs for energy independence and desire for energy independence, I guess is what I should say. I've had a good friend living in Longmont when the floods happened in 2013, and I know Boulder hit very hard then. Marshall Tires, terrible accident that is totally, you can pinpoint it to global warming. And I think there's a lot that can be done with independence of your own, with energy storage and solar to at least carry your own loads when these kinds of crises happen. I know that we're seeing a lot of interest up in Paradise, California, where those big wildfires took up the town. So these kinds of things are something that are in people's minds. Why are lithium? What's lithium all about? Why are these lithium batteries so talked about and so important? And it comes down to that lithium is a really reactive alkali metal. It happily releases its electrons and recovers its electrons, so you can cycle in and out of if it's this unstable state. It's hard to. It's a small ion. It fits into the spaces of the carbon matrix in the batteries and then supercapacitors. So it allows for higher energy density in these energy storage devices. That's why lithium tends to be the metal of choice. The other ones they're looking at are sodium, which is very prevalent. It has some problems in the way it expands inside the cells that they have to deal with. But other components of the solution are iron and phosphorus, and oxygen, and potassium and manganese and some other things that go into making these chemical structures in lithium batteries. But what's wrong with lithium batteries? Well, because they're really reactive and do this movement of electrons very rapidly and happily, they're also very volatile. Use a electrochemical process called oxidation reduction, which is referred to as redox. And that over time causes the anode and the electrolyte to break down. And that breaks down in something that looks like those stalactites over on the side picture. If those cross through the separator and in through the electrolyte to the cathode, it eventually short circuit the battery and make it worthless. And they can cause what they call a thermal runaway. Because in the cathode, there are the structures, these chemical structures that include oxygen. And when they short circuit, the oxygen molecule will be released. And so they functionally can deliver oxygen to the fire themselves without an external source. That's what they call thermal runaway. Another problem, of course, is limited supply and reliance on foreign sources for the product, particularly China. Hybrid supercapacitors, as I mentioned earlier, have a kind of a best parts of the two worlds. They have the lithium doped carbon. It's not a carbon. It's not a molecule structure that includes other materials like manganese and cobalt and things. It's strictly a storage area for the lithium ions in the carbon. On the other side is the activated carbon and its ability to move electrons very rapidly. So one side, the cathode is strictly electrostatic and the anode is electrochemical. And together they can move energy pretty quickly. Unlike lithium battery, the hybrid capacitors are chemically stabilized that employ an absorption-deabsorption reaction rather than a redox reaction. They don't cause the crystalline change, the dendrites as they call them, and the positive electrode during the discharge, the charge discharge cycles. The lithium doped carbon cathode contains no oxygen. Since it has no oxygen, there's no thermal runaway. The picture in the upper right is a supercapacitor that the folks who are describing it pounded a nail through to cause a discharge. Normally that would be the equivalent of a short circuit through a dendrite. It doesn't have the same effect on a capacitor. The cell voltage drops immediately, the temperature runs up and then slowly discharges, but never is out of control. Lithium batteries, which come in all kinds of different chemistries. You may have heard that Tesla's announced they're going from lithium nickel cobalt structure to a lithium iron phosphate LFP. So from LNC to LFP. And the reason they're doing that is LFP is a lot more stable structure. They're a little more controlled, but they're also giving up energy density, energy density and life cycles when they do that. So an LNC is a higher energy density product than an LFP. And that equates to the distance that the car can go. But metal oxide, when it breaks down, does feed oxygen into a thermal runaway. That's one of the concerns people have. So supercaps have no thermal runaway. It doesn't mean they can't burn. You know, I have a 12-year-old bottle of scotch on the shelf back there, and I bet if I broke it, it would burn if I lit it on fire. So I'm pretty sure it's the same, that's the same kind of thing. The capacitor could burn if you were to break it open, but under normal operating conditions, that never happens. This picture is a Tesla lithium ion fire in Australia. They're a big battery project. It happened about a week and a half after they installed it, but they were still testing when they went up in flames. Several things about them in general. I think we can look at this really quickly. The life cycles are much longer. The calendar life, therefore, is much longer. They have very high energy efficiency because of the electrostatic nature of the capacitors. The usable energy is 100%. There's no degradation of any consequence of a capacitor over its cycle life, so they stay fairly stable through their life cycles. The temperature range is really broad, as I mentioned early on, and they have the power density capabilities that they've always had, which is very, very high rates of charge and discharge. That allows them to be used for other applications like frequency management in the network, voltage control issues along lines and things like that in the distribution system. They're under normal operating conditions, they're non-toxic and they're non-hazardous. They don't have the off-gassing or anything like that. They have a reasonable low self-discharge rate. The supercapacitors, because of this long life capability and the ability to cycle daily without degradation, provide the lowest life cycle cost. And the life cycle cost is basically the total money spent over the time that you're analyzing it divided by the total energy delivered over that period of time measuring kilowatt hours. So it's dollars per kilowatt hour. And as you can see here, if you were to use VRLA as a valve regulated lead acid battery, they're pretty typical in the telecom industry. They have a replacement cycle of about 5 years. Lithium can go 7 to 10 years, and supercapacitors 25 or more years. But that takes the levelized cost of energy down to, in this example, down to about 8 cents a kilowatt hour. So there's benefits in different areas. I think I've covered pretty well the efficiency and the storage benefits. The profit center one is it hits really in all parts of the electric system. At a residential level, time use arbitrage, where you move in daytime solar to evening loads, peak shaving, as I mentioned, but I mentioned also frequency regulation, voltage and VAR control, which are utility applications. They can be used for black start in case of an outage, and a microgrid type of installation where they'll be the starting engine to get everything else all up and running. Many solar systems can't operate. A residential solar system without storage can't typically operate without frequency and voltage sent by the utility. So when the power goes out, your solar system goes down with it. This type of a system would bring those back up and keep them operating. And the smarter inverters are capable of running off grid. And that, of course, allows them to reduce the spinning reserve as you level out the power curve through the course of the day. Less fossil fuel fired spinning reserve, particularly for natural gas generation, is needed. So there's an active role for this solution in the utilities operations, commercial buildings, community centers, where that might be a place for emergency gatherings, lowering the need for fossil fuels in several locations. We're doing that already on off-grid, but I see that as well in the grid systems. And pretty much positioned anywhere on the distribution network where it addresses a specific issue, like, for instance, nearby a roadside EV charging gas, I guess you'd call it a station, an EV charging station for people that are on the road. So lots of applications. Just quickly, in the supply chain, you've probably heard plenty about supply chain problems. We've certainly lived through a few of them with COVID and then beyond with demand for products. One of the problems is supply. The known reserves of lithium are about equivalent to less than 50 years for EV use only. 290 million vehicles developed at current supplies. Now they're finding new supplies all the time, but it's a known reserve limitation that needs to be considered. In the US, because we don't have a lot of our own reserves, we rely on other countries, but it's about 12 million vehicles worth of non-lithium mines, lithium supply in the United States. So a lot more needs to be done here to increase the supply. And today, China refines between 80 and 95% of the lithium that's produced and used in batteries and in energy storage. And you've probably seen a lot of news about other materials. Nickel has gone up dramatically in the last few weeks because of the Ukraine war, because Russia is one of the largest suppliers of nickel, and the sanctions are going to target everybody, sell anything to anybody. So that's going to go up in price. The supply increases are significant because the demand is so high. I just read an article that suggested that the total energy storage requirement by 2030 for the world is something in the range of 12 terawatt hours. I mentioned 3 terawatt hours for US by 2030. So it's a higher number than I thought, but that's all happening. And I should mention that they call them rare earth metals, at least some of these, not all of them, copper and nickel, not necessarily, but lithium, cobalt are in there. They're not really as rare, they're just hard to extract. They tend to bond with other minerals. They don't exist by themselves like copper or iron do in there, so they're a little harder to process once you get them out of the ground. And they're spread out, often spread out a lot. So they don't find them in really concentrated places, except for maybe in the Salton Sea. They're saying that there could be a significant lithium deposit in its stable form within they bond with aqueous solutions pretty well. So as they leach out of the rocks below, they're bonded into the water and it can be extracted there. So there's some discussion that the Salton Sea may have a purpose. Mining, we need more mining, unfortunately. It comes with a significant footprint of, with CO2 and water and other things. And we need to control losses and damages of that. So just have a few more slides here and I'll be about done. just a mention of examples of other suppliers and our energy independence. We need to control our own supplies. China today mines about 60% of these rare earth metals. They process up to 95% of lithium. They develop the processed graphene about 90%, and they recycle 95% of the materials. So everybody's sending their used batteries to China and they're being recycled there. So a lot of this has to be moved into the United States for us to be able to support ourselves to a larger extent, at least within the countries that we do regular business with. Now, China is also moving towards being a raw material supplier to being an end product supplier. This improves their GDP at our expense. It gives them control over our markets. Is something we don't want to have. So in summary, let me just pop through these. To reach a 50% greenhouse gas reduction, about 2,300 terawatt hours of renewable energy is needed. That's equivalent to 75 million typical Colorado residences. I don't think you have 75 million residences in Colorado. The need for a rapid transition to renewable is dependent on the safe and adequate supply of energy storage. So energy storage supports both load curve smoothing, time of renewables. It benefits the EV charging. It benefits the ratepayers with reduced costs for running spinning reserves and expensive operating coal-fired power plants and the cleanup that goes with them. And it really helps utilities in their operations. So we need these things to be replaced, because if you buy an electric vehicle but charge it off of a coal-fired power plant supply, it isn't really green. We've seen back-to-back recent electric rates in Colorado. Utilities are struggling for various reasons, not the least of which is to how to handle new distributed generation coming on their system. But storage can help them. It could help alleviate some of those problems. So there's advantages for distributed storage to go along with the distributed generation. Lithium is currently a limiting factor. It's you know, we've talked about it. It's going to be a problem for quite a while, and that probably won't change. But there's hope that they'll come up with other alternatives like sodium to make that demand not quite such a difficult problem. Also, improved recycling is going to help, and we got to make sure we don't leave a mess wherever it is mined. Energy independence starts with reliable supplies, and renewable energy becomes reliable when you couple it with energy storage. And this can be done at all levels. It isn't just a government and a utility problem. Communities, businesses, and residents can certainly be involved. I can run a video for you. This is a pretty good one, but you can pick it up and just drop that into your Outlook or your Google web page and run it yourself in the future. It's a pretty good video that discusses this stuff. And with that, save our snow. Yeah, I'll provide all the slides. We'll send out a PDF to Empower Hour, and you guys can distribute them to whoever likes. Or people can reach out to me. My email address is in the corner down there, and I'll be happy to send things to you or answer your questions online.
So just as Todd was saying, we will post this video on our Empower Our Future website, empowerourfuture.org, and we will also make the slides available as soon as we receive them from him.
So one of the questions is, when will EVs use supercapacitors? And the answer to that is when the energy density gets substantially higher. Today, energy density in the state-of-the-art supercapacitors is about 150 watt-hours per kilogram of weight. Put that in perspective, the Tesla's LNC battery they use on their high-end cars is about 260 watt-hours per kilogram. So 100 or so watt-hours per kilogram larger, 40% more. So we definitely need to see higher energy density. They're working on those things. I've seen what they call solid state supercapacitor, which has some promise for being higher energy density. So things are coming along. I'd say in the next 3 years, you'll see a potential for much higher use of supercapacitors in electric vehicles. One place you might see them use supercapacitors sooner in vehicles is for regenerative braking and for high demand operations. So if you're going to ludicrous mode in your Tesla, it could very well be served by supercapacitors rather than batteries. That's extremely hard on batteries. So here's another question. Says, if residential solar generator reliably produces 100% of its annual demand, what size supercapacitor would be required to generally meet its nighttime variations? So let's see. So if it produces 100% of its annual demand, probably half of that's in the daytime hours. And so I'd say half could go to energy storage. That would require, so if that system, that solar system is designed at 7 kilowatts and it's making 110% during the day, then I'd say you'd need 7 times about 25 kilowatt hours of storage, which is maybe 6, like the one picture I showed at the beginning, 6 supercapacitors. The one on the right-hand side, when I showed various different projects, the one residential one on the right-hand side was 22 kilowatt hours, so approximately that size. What materials are used to manufacture capacitors? The capacitors are made out of graphite, typically light doping of lithium, but they're also using cobalt and some other things in the doping process to give them higher electrochemical capabilities on the anode. So, but for the most part, it's carbon, for the most part. The electrolyte is a non-aqueous material like nitrile, and that's the part that could be flammable if you broke them open and lit them. Are you able to throttle energy discharge of supercaps well enough for them to provide storage over a couple of days? Yes. The energy discharge is pretty much controlled by the inverter, and loads pull energy, and capacitors don't push energy. But there's a battery management system in the or a capacitor management system, maybe you want to call it, in the supercapacitors themselves that control the rate of discharge up to about 100%. And you can go as high as what they call a 2C rate in most of them. That's typically how they design them, and that would be 100% discharge in a half an hour. But most of the throttling and control is done by the inverter and whatever the demand is from the loads. So would you say, another question, so would you say this is the main reason utilities aren't adopting these faster than they are? I don't know for sure what the main reason is. Probably awareness. There are not a lot of suppliers of supercapacitors. We're one of the very few that do this. And we've only recently developed the high voltage solutions that we'll be rolling out. We have several utilities that are interested, so I think you'll see more of this in the future. It's just an awareness thing more than anything, I'd say. I made a good case, but I didn't explain what's holding back the technology. The technology is being held back both in the improvement of batteries and in the improvement of supercapacitors in the chemistry side of things. The best way to develop these hasn't really been formed. So a sodium-based capacitor, and the price, I suppose, is also this. Sodium-based battery, they talk a bit about those. They have expansion problems when they charge up that make them difficult to manage. Their sodium's widely available, so it'd be a really nice battery if you can make it work. but there's other things happening there as well. Part of it just has to do with promoting the technology. An ordinary person can promote the use of supercapacitors, I think, best by having them running and believing in them. That's what I think. If you look at that video, you can see that the presenter on that video is clearly impressed with supercapacitor capability. And we have a lot going into telecom that is replacing lead acid for the very reason that it has shown to be very durable and has had really good response with respect to maintenance and longevity.
So Todd, I think we've got time for one more question.
Okay.
Maybe Leslie's.
Okay, sure. Will supercapacitors be able to bid into the XL RFP that we expect later in 2022, proceeding whatever? We're looking for more storage and peak shaving. Well, I suppose so. We generally don't bid utility RFPs because sometimes they're really onerous. So it depends on what the conditions are of the RFP, whether we would consider bidding into that. But yeah, there's no reason. I've reviewed and even submitted to some RFPs, preliminary the RFIs, but subsequently I didn't bid the RFP. Some of them are massive. I looked at one from Long Island. It was something like 2,800 megawatt hours of energy storage. So they're massive. So the only thing holding back the bidding into these RFPs is how large they are and what kind of hoops we have to jump through. Right now, we can sell pretty much everything we can get our hands on because of supply issues. But that should be opening up this coming year, and we hope that that'll improve things.
Thank you, Todd. That was fabulous. I learned a whole lot. It was really interesting, and I'm sure, I know we've got more questions that we didn't have time to get to, but we will put this video on our website, and we'll also put the link that you had in that slide on our website so people can follow it and learn more about it. Is there a company web address you'd like to mention for people who are interested?
It's supercapenergy.com. So down in my email address, just put www dot in front of that. And
okay, and it looks like it's on your slide here too. And
yeah, it's on the slide on
Energy.
the lower left here.
Great.
Yeah.
Thank you, Todd. It was really wonderful to have an expert enlighten us about this that we've heard a lot about, but I know for me and probably for a lot of other people, I really didn't know a whole lot more than when I was building Heath kits back 100 years ago. But thank you very much. And for our audience, thank you for showing up. And I just want to let you know that we have some very interesting, exciting upcoming Empower Hours. On April 21st, we'll be hearing from our friends at Cultivando about the status of the Suncor refinery, how the monitoring is progressing, what problems they're having, and what successes they're having, and expect a special guest appearance from Delta, and from on the May 21st, we've got a Boulder County candidate forum for the Boulder County Commissioners on May 12th. So April 21st for Suncor and the May 12th for the Boulder County Candidate Forum. So on behalf of all of us here at Empower Our Future, thanks again to Todd Pistorese and to all of you for showing up, and we'll see you next month.
Hey, wait a second, Chris.
What?
We can, Todd's willing to stick around for a while. We can take more questions.
Oh, wonderful. Good.
Sure.
So we do like to keep it to an hour, but Todd, you're willing to stick around so we could just follow up with more questions from the Q&A?
See what I can have here. There's a question from My little town of Hilo, Hawaii. Lee Ayers writes, what about the test system in Everett? Well, the test system in Everett's 90 kilowatt hours of storage and 40 kilowatts of power. So it's basically a 2-hour system. They can run their load for 2 hours in the building. It's really there to test the cycling of these modules at high voltage. So instead of putting them in like a telecom site that we put in parallel, and they're all 48 volts. 48 volts is the native voltage for telecom systems. Residential systems are, the vast majority of them are 48 volts DC on the energy storage side. For the utility scale work, we need to get up into the range of 600 to 800 volts DC. And in order to do that, we put 12 of these modules in series. And then we put multiple in parallel to get up to the capacity that we want. So that's been running for about 2.5 months, almost 3 months now, and looks really good. So we have two utilities that want to do something similar. We have one down in Florida that wants to do a smaller system, a little bit bigger than what we built in their customer experience center. And we have one in the Tennessee Valley Authority that's going to do a pilot of about somewhere in the range of 1 to 1.5 megawatt hours, and use it for specifically for peak shaving for the distribution company that buys their power from TVA. And they pay some expensive prices for peak power, so they're looking forward to testing that. That should happen they should be running this summer. United Power is our electric supplier, and demand charge is $1.50 per kilowatt. So on average between 8.8 kilowatts and 4.94 kilowatts. Question, how can SuperCaps reduce overall cost? Well, if it's like most utilities, the peak demand that you see on your bill for kilowatts is based on the highest 15-minute average during the month. And so you find that peak, and you carve it off you shave the top of it off. We do it more simply than that. The system that's at the MRM, they set it at a specific amperage. They say, okay, our peak last month was 20% above our average, and so we're going to run and that turns out to be, let's say, 25 amps at 480 volts AC coming into the building. We're going to limit anything over 15 amps and supply that with the supercapacitors. And that's how they operate theirs. They pull about 80% of the power out of their supercapacitors every day, doing peak shaving as the machines go off and on. And then at night, when everybody's gone home and it's out, they recharge those. They do mitigate it to some degree also with some solar that they put on the building, but that's how the supercapacitors are used. And that reduces their overall cost because it lowers that peak. Once the peak's lower, the kilowatts that are multiplied times $1.5 go down.
Hey, Todd.
Yes.
We've got a couple of audience members have raised their hands.
Okay.
So John Calley, if you can unmute yourself now, you can ask your question or make your comment.
Yeah, I actually figured out later that I could type in my Q&A, but my question is, capacitors are known when they discharge, it's an exponential decay, and the voltage very quickly drops and has a long tail at low voltage. So does that limit what the capacitor can provide? Is there a voltage level below which the capacitor, it's too low to be used? And how's that handled? Thanks.
Yeah, two things. So a traditional standard capacitor does have a very rapid discharge curve. So voltage does drop pretty quickly, and they're designed to, just do quick bursts. So it typically doesn't affect what their application is. Supercapacitors, because of the hybrid nature of them, they have substantially more stable, what they would call self-discharge, less than 2% a month. We've had supercapacitors shipped in, and even the ones I put in my home in Hawaii had been in the box for 9 months or longer before they finally were installed, and they were at when their peak voltage is 54 volts, 100% charge. They were at 51.5, 52 volts after 9 months. So they hadn't lost significant amount of power at all. But the voltage range is managed by the BMS to some extent. So the capacitors we see do have a drop off, whereas for those that don't know, a lithium battery, for instance, has a fairly stable voltage with a rapid drop off at the tail end when it finally runs out of power. So they hold kind of a constant voltage in batteries, chemical batteries. The hybrid supercapacitors do trail off, and they drop from 54 in the case of the ones that I have. Newer ones are a little different voltage range, but from 54 to 44 volts is their operating range over the course of the ones that I have are delivered 3.5 kilowatt hours in that duration. Now that can go faster or slower, depends on what the loads are. You can pull those down completely in a half an hour if that's the kind of, if you have a 7 kilowatt load, for instance, you would pull them down that fast. But they're fairly stable, and part of that has to do with the BMS. The other part of it has to do with the way they architect the hybrid supercapacitor. The lithium doping means that part of the process is electrochemical and part of it's electrostatic. So the traditional capacitor you're thinking of is a pure electrostatic item, and these guys with the electrochemical component are much more stable in their voltage.
Okay, let's see if Leslie has another question. She had her hand up.
Thank you. It was awesome, Todd. Thank you so much. Leslie Lustrom with Empower Our Future and a few other things. I'm a little embarrassed to ask this question. You don't have to answer it now. When I looked at your slides, I got confused about which was the cathode and which was the anode. In slide 19, the lithium dope carbon was the cathode, but earlier on, like in slide 3, it looked to me like the lithium dope carbon was the anode. So you don't worry about it now, or if you're at whatever, but I'm just curious, and I wanted to get it straight.
Yeah, I can tell you that the lithium doping goes into the cathode to enhance its capacitance, but it's the anode is for the most part the cathode is electrostatic, and the anode is electrostatic and electrochemical. They're a little bit confusing, and some of the pictures were reversed too, so that might have really screwed it up. But I tried to pick up ones that are always the anode was on the right and the cathode was on the left, and the anode is the negative terminal and the cathode is the positive terminal. I'll double check which ones those are and see if they messed up. But try not to.
Thanks a lot. Thanks, Paul. Sorry, everybody. The old chemist.
Okay. Well, I'm an electrical engineer, did I tell you that? So, you know, when you start talking about chemistry.
Thanks so much, Todd. It's really exciting.
Thank you. So I have a question here from Ron Horstman. Thanks, Ron. Yeah, thanks for, I'm glad you liked the presentation. He says, since we're at the crossroads where the cost of renewables and supercapacitor stationary storage is cost effective, should this type of storage be required in new construction? Gosh, that's a good question. Good question. I'd say sure, absolutely, it should be. but honestly, I think they let the builder and the owners make those decisions. The builder is going to go strictly by the cheapest thing they can put in. If I know anything about builders, I apologize to anybody out there who might be a builder. I've built enough things of my own. I know this for a fact, but that unfortunately isn't necessarily best for the longevity of the system or for its usability as an arbitrage tool. If you really want to exercise these things, lithium batteries are not what you want to use, in my mind, because well, 2 reasons. They have a better purpose in life to be in a car than they do to be in a stationary storage location, and they do degrade about 30% over their lifetime. And they also, all of the lithium guys put in a cycle throughput disclaimer on their warranties. And so if you were to cycle it, 80%, which is kind of their recommendation, no more than 80% every single day, they wouldn't last for more than 4 or 5 years at the best. So that's my concern with the cheap, going the cheap route, and that might be lithium battery. Now, a Powerwall is fairly expensive to buy and install. I've seen pricing in the $12,000 to $15,000 for a Powerwall. And a Powerwall is 13.5 kilowatt hours of energy storage and a 7 kilowatt built-in inverter. So it's a pretty expensive item to be cycling heavily if you think you're only going to get 5 years out of it. All they're going to warranty is the product, not the removal and the reinstallation of a new one. So if it were to fail under warranty or end its life under warranty, you still have a lot of expense related to taking it out and putting in a new one. So I think that they should be using supercapacitors because they have a longevity that would be well up into the 20 or 30 years, but also most residential homeowners, I think, do they still stay in their houses on average about 7 or 8 years? Maybe the moving around part has slowed down. I don't know. Okay. Let's see here. I think I answered those 2 questions. SuperCaps have been around for a while. They were strongly considered for wind turbine pitch control system, but didn't catch on 10 years ago. How long have hybrid supercapacitors been available? Would you compare them to the 10-year-old technology? They have been around for at least the earlier versions of about 3 or 4 years. The earliest ones we've seen were what they call an 18650. It's a cylindrical. An 18650 just means 18 millimeters diameter by 65 millimeters long. So it looks slightly bigger than a AA battery. And they were lower energy density than we're seeing today. They're getting a lot more clever about the carbon structures and about how they dope these things and the electrolytes that they're using. But I think they would be a viable solution for this application in that they have a much higher energy density and the rapid response charge discharge capabilities are fairly nice. We've seen interest in them just for frequency control on the network. So that's something that's possible. Let's see. The thing is dancing around on me. Why is it doing that? Is it my fault? Woody, you asked why they're not more ubiquitous, and I'd say because of supply. We're fixing that. We're working hard to fix the supply issues. We're actually there was a question earlier. I think it bounced out of my display, but there was a question about investors and financing, and we are working with the manufacturers to bring manufacturing to the United States. And there is quite a bit of interest for locating it in Colorado and probably other states. I mean, it's something, and it's not like they need one factory to do the job. There could be, based on the amount of energy storage that's required, there could be a dozen factories making these things in the United States. I'd like to see it. I'd like to see it moved here and that portion done by the U.S. because it would eliminate a great deal of the supply chain problems with shipping and waiting in ports. I think we had supercapacitors sitting offshore in LA last year for something like a month or maybe longer. There was something in the range of 30 to 50 ships waiting to get unloaded in Long Beach, down in California, where when the COVID was at its peak and there weren't enough workers, enough drivers, and enough anything. So it would be nice to have them manufactured in the U.S. And there are very interested investors in this product. There's a question about how the cost compares to that of pumped water storage or compressed air. Off the top of my head, James, I don't have an answer for you on that. I have to go back and review what their cost and levelized cost of energy. Both of those actually have fairly long lives, so they would be viable products for a number of applications. Most of the time, the supercapacitors tend to be picked up for the rapid response type of capabilities that they have, but they do have long energy density capabilities as well. Things like flow batteries, compressed air have much slower charge discharge cycling with the C rate, but they have applications, and they all be, from the very get-go of this presentation, I said it's not about replacing another energy storage solution with capacitors. It's about having enough energy storage solutions in total to cover the demand. So all of these things will be employed, I'm sure. RJ Harrington asked, do you envision grid edge supercap DERs could be integrated into the Marshall Fire Impact community? And yes, I mean, I think distributed energy resources with energy storage it really is best to put these products and these solutions as close to the loads as possible, because you get away from the losses in the transmission and distribution system that are inherent with large-scale generation. So back in the day of Edison, when they were arguing over AC versus DC, and you know, Tesla was saying one thing, the real Tesla, not the car guy, and you know, Edison saying another thing, and they're pushing these different solutions. Nobody was thinking about, you know, scaling up to really, really large generation stations. They're looking at localized power supply, localized generation. And there are a lot of advantages to that, but the utilities industries has an economy of scale, and they've just kept making things bigger and bigger and putting them on larger transmission systems and distribution grids. And realistically, distributed energy is coming back around. And you can, I mean, every home that has a smart inverter and storage unit is what we call a nano grid. It's its own microgrid. It's self-contained. My system went off in Hawaii for 5 days. It went on solar and storage while Hurricane Iselle came through in 2015 or 2016. So yeah, they're viable for distributed energy, and I would encourage those as a resiliency solution or a microgrid. If you can get the utility to cooperate with you, you can put microgrids, but you have to use their grid to do it. So that's something that the utilities need to realize. I know Commonwealth Edison in Chicago has built some microgrids. I don't know if, I haven't talked to them out there whether they consider putting supercapacitors in. I probably should reach out. That's a good question.
We got another question from Leslie. Where are supercaps manufactured now?
They're manufactured in a few places. There's manufacturing where we get the ones that were in the displays that we showed you here from Kilowatt Labs are manufactured in Dubai, in the United Arab Emirates. There's also manufacturing in China, and we would very much like there to be manufacturing in the United States. Inverters that we use are manufactured in the United States. And there's a company called Oztech. I'll do a shout out for Oztech Corp. And they're in Massachusetts, and they make a wonderful 40 kilowatt PCS, power control system for energy storage. That's the one that we used in the system that's in Everett. It's a very, very nice product. So we're partway there. I'm hopeful that we'll get supercapacitors manufactured in the US in the near 2-year window here. In the near 2-year future. Oh, here's one. How many small capacitors can be stacked in parallel modules in a rack in a home? Well, the one picture I showed were 6 capacitors, but that's a kind of a narrow rack mounted unit that is a little taller than the others. We can see in a typical 8-foot high ceiling area, you can put easily 8 or 9 supercapacitors in a rack. And they're typically anything from 2.5 kilowatt hours each up to 7.6 kilowatt hours each. So you can put a sizable amount of energy storage in a 23-inch wide by just under 8-foot high rack. Lynn Siegel asked, can they be used in a microgrid? Absolutely, yeah. The inverter I mentioned from Oztech is capable of black start, of grid forming and grid following, voltage and bar control, a lot of features. So the energy storage type that's used by the PCS is probably less important to it than what the capabilities of the inverter or the PCS are. So I would say absolutely, and that's where a lot of these are going to go in the future for resiliency. And you'll see them. I know I've talked to utilities that want to put them on long line distribution systems to support voltage, particularly if you drive your car home and you're 10 miles out on the line and you want to plug it in and pull, 5 kilowatts out pretty quickly to recharge your vehicle before you go again. If there's enough people on the circuit that want to do that, then there's going to be voltage issues on that circuit. So the utility or the homeowner could mitigate that by using energy storage to take some of that load. How does adoption compare to other countries, in other countries compared to the US? Well, Brian, I'd say pretty good. We see a lot going on particularly in places like Africa, of all places, because they have a lot of villages with no power at all. So, but that's something that we see them selling them all over the world. The US is obviously the biggest market in the world, so we're probably have the largest demand in general, but European countries are picking these up as well. Scott, that's a great question, because I tend to overlook the jargon. Scott asked me, what is black start? And black start is when the whole system goes down, how do you get things running again? Something has to come on first, and it has to establish the voltage and the frequency in order for other things to start. If you just have solar on your roof and and it's not a smart inverter, it's just a sunny boy inverter, it will not run when the power goes out, because it's looking for the grid frequency and voltage for it to operate. So if you and your neighbor could make a mini grid, your neighbor could fire up their smart inverter or their or something. Last inverter would create its own frequency and voltage, and then the neighbor's sunny boy would say, "Oh, I see frequency and voltage," and it would start as well. So that's black start, something that's going to start everything to begin with. And so the PCS can create frequency and voltage and form grid forming. They can literally form a grid. And then they start to add the loads and the other generation supply. It's still a tricky process, because you can't put on too much load too quickly when you bring these back together, these systems back together. It's something that the utilities do all the time, even with the regular system, called the cold load pickup. And they'll have to go out and sectionalize the lines, disconnect portions of the line on the way back to the substation, start it at the substation, pick up the closest loads, because they're all going to come on at once and they're going to be a big load. And then they go down the line and start to close in additional disconnect points and slowly bring the system back up. And that's something we did back in the days of big winter storms, called cold load pickup. It's very similar to black starting. And Steve Douglas asks, can a capacitor in a home be used as an inverter on a level 3 charger, DC to DC? If you have the capacity in the DC to DC charge controller that you can go directly from the supercapacitors into the vehicle's charger, yes, it could be used that way. The vehicles are typically at 400 volts, something in that range, I believe. So you would want to do a DC to DC coupler that is running off of a higher voltage supercapacitor system than a 48 volt system. So it'd be something not maybe as big as the system in Everett, but something that's in the range of 8 supercapacitors in series. But yes, it could be done. All right. I think that's it. If I missed your question, feel free to email me.
Thanks
Great.
once again, Todd. We really appreciate it. And thanks once again. And as you're seeing on the screen, here's the reminders for the upcoming power hours. Oh, it went away. Once again, the April 21st, the Suncor refinery status update, what's happening down in Denver from our friends at Cultivando, and May 12th, candidate forum for the Boulder County Commissioners. And with the Suncor refinery, we expect maybe a guest appearance from Dr. Detlev Helmig. So thank you, everybody, and please tune in next month. Take care.